the AutoCAD file where the circles are circles are drawn with the radius having the frequency. The radius is 880, means frequency is 880, the note is for 880. If the circle is drawn with 680, then its frequency is 680. Everything here is drawn above 440, that is, the notes are the higher frequency. Here you can see the notes are at the C5 level, and this music is generated from this CAD file. Listen the music first and look at the patterns, the hash patterns and the line segments here. The line segments are taken from the trigonometry expressions. All of these things are triangulated forms. In our previous videos we have explained everything, and this Midi file that you are listening, that is playing in the background, is generated from this CAD file. I will show you how can our simulator design this kind of music out of these geometries. In our previous video I have shown you that how to generate this kind of image from the existing Midi file, and through the geometrifying trigonometry algorithms we can do the reverse also. Today we will explain how to think about these kind of things. First of all, the circles are the frequencies. Circles are having the radius as the frequencies, and the patterns which are repeating here, which has a musical meaning, and the pattern is done with the polar array, and so the same pattern, bit pattern, is continuing, and you can see in the Midi file. So listen this music first and see these bit patterns. Examine these bit patterns. Listen it carefully for 2 to 3 minutes and try to observe its meaning. This one is having the radius of 680, that is the frequency 680 Hz. This one is having the radius equal to 880, that is the 880 Hz. This is the radius of 1080, so its frequency, the line segments which are lying here are having 680 Hz, and this circle is at the 1280, so it's the line segments lying on this line segment on the circle will have the 1280 frequency Hz, and the notes or corresponding notes, you can see the maximum of these are the C5, and those are calculated in that way. You can cross verify, and if we do the scaling of this with respect to 0, 0, suppose we do the scaling of this with reference to the base point 0, 0, 0, and if we set the scale factor as 0.68, then the radius of all these things will reduce, and we can get another Midi file whose base frequency will have the different radius 598, and I was varying these scales by scaling these and generating this kind of music, so we could get the different kind of music from the same EXF file differently with different note positions, and all the note positions changes as we scale that EXF file. Listen this first, and from that try to understand the geometry parallelly. Listen to this and parallelly try to understand this geometry, and try to understand this geometry, and you can calculate these things here. I got the idea from Midi CSV, but I have not used Midi CSV here because Midi CSV was not giving me full freedom to change all the kinds of frequency calculations, and Midi CSV needs a lot of typing, and I was trying to convert everything from geometry directly from AutoCAD geometry, because these kind of geometries we get in engineering drawings, and we get this kind of geometry from the vibration data also, and I take help of Midi CSV sometimes to cross verify, and doing the things with Midi CSV takes a lot of time when we try to convert this kind of geometry to the Midi files. I use Midi CSV, but I will explain some more kind of calculations here through our Geometrifying Trigonometry simulator. Even I have to use the Midi CSV files. I get the line segment data from the Geometrifying Trigonometry simulator, and from that line segment data I get the possible frequency positions and the duration of the nodes. Calculating the duration of the nodes is not so easy, and typing all the data to the Midi CSV for the patch changes. And here you can see lots of music are playing on the single channel. On the single note we can see multiple number of instruments are playing. After listening this thing properly, you can understand that what we are doing here and how we are thinking on these. I will show you how to run this simulator to get this kind of music out of this geometry, and to and fro getting this kind of geometry from this kind of music. I have already explained the reverse process, that is converting the geometry, the CAD geometry from the Midi files, that was explained in our previous video. And in our current video we are going to show you that how to convert and how to think about the conversion of geometry data to the Midi data. And Midi data means a music data, and for every several kind of conditions as per the listening needs, or sometimes for specific purpose, we can generate our own Midi files with our contextual geometry data to represent some kind of geometry through the listening of the musical notes. We can think of this kind of things. Listen it carefully and see the image here, and then you will understand that how the geometrifying trigonometry concept is different from the normal trigonometry algebra like things, and how geometrifying trigonometry representing everything as a line segments, and those line segments have a direct relationship with the Midi notes and the note durations, the note frequencies. The slopes here can automatically give us the assignment of the patches, that is the instrument numbers, and the line segments having the lengths which signify the duration of the notes. I will not talk for few seconds. Listen the things and observe the geometry carefully. I have already explained to some extent. You can listen these things and you can see that in our events, and these at the below level we can see there are several pitch bends, and I have implemented the pitch bend effects also, which are done through the layering here. The layers of the line segments, the colors of the line segments can give us different kind of velocities control. We can give the different kind of key pressure. We can change the pitch bend with the geometry itself, and trigonometry expressions through the geometrifying trigonometry gives a lot of information about every line segment, and every line segment can have a musical interpretation also, and we are trying to show you the interpretation here. I should keep listening, give you some time to listen and see this image. That is not image, that is a drawing file, engineering drawing file, and you should listen it and see the geometry also. Let us try to prepare a small Excel file here and try to demonstrate you how to think about this kind of music normally with engineering drawings. Circle 0,0. We are taking a frequency here with these are the instruments which we can assign. These are 1, 2, 3 are all the patch numbers. These come from the slopes. We have calibrated the line segment slopes to 360 degree with the calibrated values of these, and we can use the modulus function also. We can use some other factor calculation also as per the sentiment of the music as we want to design. We will explain it. Suppose we close these text files and let us try to show you from the beginning. Like this is the Geometrifying Trigonometry cursor which takes the Excel-like formula for the trigonometry expressions from our school days, from our school books, and then we can generate the geometry. These files automatically open, and I was trying to make some experiment with these, and you know that this size was bigger. I was making some space to implement the geometry here, and we can change the angles, to change the shapes of these. We can change the command value, say images changes and angles changes and the objects and their behavior changes. We have done several videos on these explanations, and you can see the theta changing, the seed angle changing. There are several line segments and there are circles also visible. These are the node circles, these are the hard circles, and the calibrations are possible. Stage-wise constructions that we were showing in our previous videos. I will make this screen bigger since I was planning, but it is looking little smaller. I was planning for the musical notes here, but no, the geometry is looking smaller. Here the separate tab is here. Try to see the explanation of these things. Try to calculate yourself, and the meaning of these things are written here. I will explain it. Suppose for the reverse calculation, suppose if you have a time duration given for your music, suppose 11,000, suppose 11 seconds, 11,000, that is the value in the microsecond. The BPM is given here. Suppose it is 120. If we want to make it as 180, then it will calculate the bits as the integer. The 350, this value is to set here. Say we are putting it as a 480. It should work good. Now the message is saying to make everything proper, we should make it in that way. We normally see it as a 4x4. And what does that mean? The 4x4 is a separate kind of calculation which gives us a note per bit, the note bits per measure, that is on the 4 in the numerator, and denominator is giving us another value, that's the note per bit, and this value gives us a ticks per note, that is a tick per bit, that is ticks per quarter note, and these are given here. Suppose tick, tick, these things you can see the tick, tick, which means there is 120 ppm, where two ticks give us two bits give us 1 second, and so 120 bpm is covered here in the music that you are listening here. Now with these odd kind of calculations or even kind of calculation, suppose 3 by 11, it's an odd kind of calculation that is in the musical note. We don't see it in that way. Suppose we want to put it at the 168 bpm. Here we want to put the ticks per quarter note as suppose 338, which is very odd. This is very creative music. Okay, now we want to do it with the 368, and see, suppose 226, 221. Suppose this is a very odd value. 617 is it is suggesting us. Now, okay, whatever it is, but I will show these calculations also. The microsecond per beat is there. It is going out of this screen. This screen is smaller. I have to adjust the other tabs, and to do that I was making this space. Let's see what better we can do with this calculation. Let's see how can we think about these kind of things. Say 440 is the hertz value, and it is generated here. Control S, simple music. Simple. So it's a simple thing. Let's say we take the notes with the hertz values of say 311. Now 261.63 is another circle, which is the middle C. Here the C4, middle C 261.63. Let's take one circle at C, here CLE 260, which is the value of 261.63. Say we are taking the circle 261.63, and sorry, Z space, E space, circle, center 0, 0, 261.63. It's the another circle. Wait here, and suppose we want to make one higher frequency with say C5, that is 554, or we can take it as the G5 783.99. it sounds good, 783.99. Suppose we want to put a circle at center at 0, 0, 0, and 783.99 is the radius. 783.99 is the radius. So 3 circles are taken. These are the 3 references, and here suppose we are taking a line 0, 0, 0 to the ortho on. Here we will delete this line, otherwise it will take a long note due to this L. Suppose I'm doing the object snapping here. Each note length can have a very small value, and with that I can take here the line for the reference on this circle. Suppose I am taking another line here. These lines are automatically coming from the geometrifying trigonometry triangles. Suppose I am generating this zero comma zero comma zero is the center, and then I am drawing another line here, line here. Suppose it is taken here, and on the three circles I have taken 3 lines. I am deleting these reference lines, and also I am deleting these reference circles. These are not necessary when the line segments automatically come from geometrifying trigonometry. These circles are irrelevant. Now we will use the array command. This array command is also irrelevant for geometrifying trigonometry because those line segments automatically come from the geometrifying trigonometry expression parsers. If you type the data in the Excel-like formula, it will parse it to the pictures with the line segments. We are selecting these objects, and the center is taken at 0, 0, 360. Total number of item is suppose 100. Angle between it is automatically calculated, and the polar array will form, and the polar array is formed here. The file name is called the simple file name. Okay, we will copy this path, we will go to here, we will fill the necessary data here, and then suppose we want to do it the 11 seconds music, that is into 1000. Then we select the file name, here this one is a simple.dxf. Its extension should come automatically, but it is not coming. It is a simple.dxf. Okay, this is a simple.dxf, and you can see there is no MIDI file here. In this same path, I am choosing the simple.dxf here. It will calculate and it will generate the MIDI file here. Total nodes 300. It is generating the file. It is generating the report, that how many line segments it has found, how many node velocity it has generated, and from these values my system is little slower, so it takes long time to generate the MIDI files because it calculates the patch numbers, it calculates the value there, it assigns the note frequencies accordingly, and the MIDI file is a 74 KB. The file is generated. Total length of this is like this, and it is generated here. Okay, now we can see that how this MIDI file sounds like. Suppose we want to open this file, Control O, suppose this one is the file generated, this one is another hard coded file. No, this was the file that I was practicing with, but this one is a simple file, simple DXF BPM 168 that we have filled there with 221 TPQN that you have seen. I'm opening it and I will try to play it. You can see the effect of the peak bends. C5. Okay, so you have seen that how to think about the music out of the trigonometry and out of the geometry, and today's session was on this thing. Thank you.